Hi y'all, so today I'm just going to go over the Chapter 4 group work, and this is to help you prepare for your quiz tomorrow and help you get this information solidified. So first, cyclohexanol. So cyclohexane is a ring, and when there's a cyclohexane, actually you don't have to, with cyclohexanol, that's the only substituent, you don't have to put the locant on it because you assume that it starts at 1. It's like a weird one-off rule. If you're not sure, just put the 1. I would feel better about you doing that. Okay, the next question, 2,2-dimethylpentane. 2,2-dimethylpentane. Pentane is 1, 2, 3, 4, 5, and then I see the 2,2-dimethyl, so that's where I did 2,2-dimethyl. Hept2-ene, so 1, 2, 3, 4, 5, 6, 7 for heptane, but it's 2-ene, so 1, 2. It doesn't say cis or trans, but if I was trying to draw cis, it would look like this: 1, 2, 3, 4, 5, 6, 7. Cis methyl hex2-ene, so 1, 2, 3, 4, 5, 6. So hex 6, 2-ene. I put the 2 here, and it's cis, so these are on the same side. A lot of y'all work. I was kind of surprised by this because we've done so much cis and trans, but a lot of students were kind of like had a hard time drawing the cis. But if you're not sure, just check yourself and like cover it up. And are these, like we did before, are these hydrogens on the same side or not? If they are, then it's cis. If they're not, then it's trans. Trans 2, trans oct2-ene for all. So I'm going to start with just the backbone. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8 is the parent chain. Trans oct2-ene, so 1, 2-ene, and this is trans, so that makes life easier because it's already trans. And then for all. Okay, and then last but not least, well, the base is the same. 1, 2, 3, 4, 5, 6, 7, 8. Trans 5 chloro, 6 fluoro, 5, 6 dimethyl, oct2-ene, and it's trans, so it looks like that. So that's how I'd go through those questions. Write the name for each of the following molecules taken from OChem as a second language. I'm actually gonna, can you turn this on? There we go. Okay, so the first one, I'm going to find the parent chain. I think it's 8 is the longest one I can find. And I noticed students were having some trouble kind of maybe telling the difference between, let's see, can I find anyone longer? 1, 2, 3, 4, 5, 6. 4, 5, 6. No, that's the longest one. I noticed students were having trouble kind of telling the difference between the parent chain and the substituents. So once I found the longest chain, I highlight that chain if I'm not sure. And then anything that's not highlighted is what you're going to have to make note of. So right here, this is one, this is one, and this is one. So I start out by just writing for this, I would say the parent chain is octane. And then I see that it's 2-ene. And actually that's trans. And then 1, 2, 3, 4 ethyl, 5 methyl. Now, because the double bond is higher priority, we want it to have the lowest number possible, so that's why I'm starting from that side. But if we were to number from this side anyway, it would still be 4, 5, 6. And so 2, 4, 5 is better than 4, 5, 6 anyway. But if you're ever not sure about the numbers, You can always number it both directions. I usually use different colors to number it both directions, and then I just pick one. So if I combined all this, I would say trans. Let's see, ethyl comes first. 4 ethyl, 5 methyl, oct, 2 ene. Okay. And then this one, I also got a lot of questions about whether the parent chain starts right here. And the answer is no. The parent chain is going to contain the alcohol, meaning it has to be directly bonded to the alcohol, but it doesn't have to start at the alcohol. This is the longest chain that I see, so I'm going to number that 1, 2, 3, 4, 5, 6, 7, 8, 9. Alcohol has a higher priority, so I'm going to start from that side. If we numbered it from the other side anyway, it would be like 1, 2, 3, 4, 5, 6, 6 and 7 for the substituents, so that's not great. So this is nonane. Oh wait, sorry. The parent chain is nonane, and we have 3 all, and we have 4 ethyl. So we would combine that to be 4 ethyl, nonane, 3 all. You can also do 4 ethyl, 3 nonanol if that's easier for you. I don't have a strong feeling either one is accepted by IUPAC, but I personally preferred it to be right in front, but either one is correct. Okay, so this looks like the longest chain I can find. 1, 2, 3, 4, 5, 6. So that is hexane as the parent chain. And we're going to start from this side to give the triple bond the lowest number. So these are our substituents. So we have, and also if we went this way, it'd be 1, 2, 3 anyway. So 2 is better than 3. So we have 2-ine as 1 and 4,4 dimethyl. So if we combine this all, it'd be 4, 4 dimethyl hex 2-ine. Okay, and on this one, I meant to change this to be OH, just a single bond to OH, so I messed up. But so the ring is going to be the parent chain here. 1, 2, 3, 4, 5, 6, and it's going to start 1 at alcohol because that's the main one. So we have cyclohexane as the main parent chain. We have 1 all, and we have 4,4 dimethyl. So technically, I think with this weird cyclohexane rule, you don't have to put that 1 all, but I do. I'll go ahead and, well, it'd be 4,4 dimethyl cyclohexanol should be like the actual proper answer. But if you did this, I probably won't count off because it's kind of just a weird rule. But some professors might, so don't just do what I do if I'm not your professor. Okay, and then 1, 2, 3, 4, 5, 6. That's the parent chain. It looks like hexane. If we numbered it from this way, you'd get 2 chloro, 3, 3 dimethyl, 4 fluoro. I think if you numbered it from the other way, 5, it would be 3, 4, 4, 5. So the pink way is better. So this would be in alphabetical order. It'd be 2 chloro, and then we're actually going to do the 4 fluoro because we don't count the di in nomenclature. 4 fluoro, 3, 3 dimethyl hex. Oh man, I ran out of room. Hexane. So that would be the name. Okay, draw the Newman projection of 1-bromo 2-chloropentane around the 1,2 carbon. So I did not make you have to do wedge dash, so you can kind of pick what you want to do. So I would first start by drawing the pentane. 1-bromo, 2-chloro. So 1, 2, 3, 4, 5. 1-bromo, 2-chloro. And you can pick which side you want to do it on. Does not matter to me. I did not make you do the wedge and dash. But I'll just leave the bromo in the plane of the page like that and draw in my hydrogens. And then we'll make this a wedge, and just for fun, we'll make this H. So that's how I'm going to draw it. And you're looking from the 1, 2 carbon. So the one that comes first is 1. So we're going to look from 1 down to 2. So my bromine will go straight up. And then I'll have 2 hydrogens coming down. And then in the back, see, my chlorine would be on the right and my hydrogen would be on the left. And then I'd have 1, 2, 3. There we go. So this is the Newman projection. And then I'm going to draw all the different conformers. So I'm just going to rotate only the front one. So this is 1. Oh, there's one in between this where it's eclipsed. My bad. So for eclipse, you draw it right next to it, even though technically it's on top, just to show that it's like what's going on, kind of. Okay, and then it would move. So we moved this. First, we rotated this whole thing by like, I guess, is that what, 60 degrees? Or no, 35 degrees. Basically, we rotated it to be even with that to get here. And then we rotated it this to this spot right here to get staggered, or the bromine right there to get staggered. And then we'll actually get another staggered conformation here where we're rotating the H to be on top of this chlorine. And it looks like then the bromine will go down here and the other H will be on top of this hydrogen. And then we'll rotate it again. Let's see. That's CO. And then we'll rotate it again to where the bromine will be on top. Oh, wait. I just drew the wrong thing. It needs to be an eclipse conformation. I don't know why that was hard for my brain. H, CO. And then it goes right over the top of it. So the bromine would be here, H and H. And then if we rotate it again, it would get back to this first position. So this is 1, 2, 3, 4. You don't have to use Roman numerals. I just did because they were here. 5 and 6. Look, I just, for some reason, drew that as regular 6. And now we're going to find what is the highest and what's the lowest. So I would actually say this, all the eclipsed are here, here, and here. And these will, on average, be higher than the other ones. The biggest groups overlapping each other is the worst. And so actually, I think chlorine is lower down on the periodic table than carbon. So chlorine and bromine would be the 2 biggest groups. So I would actually say this is the lowest energy. Or what? Not the lowest. The highest energy. Sorry. Highest energy. here where they're eclipsed, so that's the least stable. And then when these are completely opposite of each other right here is when I would say it's the lowest energy, so the most stable. So I think this is the most stable. Okay, and now I'm supposed to draw the conformational analysis. I'm actually going to draw this on a separate page that it would be easier to see. So we know that in general, your two most stable is going to be, let's see, this one being numbered at 5. And then we would go all the way back to get to 5 again. So 5 is the most stable. And then 2 is the highest energy right here. So 5 is the most stable, 2 is the highest energy. So I'm just going to go through 5, and then 6 doesn't have the largest groups eclipsed, but it is eclipsed to some degree. So 6 here. And then we go over to 1. So 1 has the two biggest groups somewhat close to each other, but not exactly eclipsed. And then 2, the two largest groups are perfectly eclipsed, so that's the biggest. And then 3 is more similar to, actually, I think 3 would be a little bit lower, closer to 1. And I think then this would be 4. So it's like you can kind of see the pattern where the lowest ones are the staggered and the highest ones are the eclipsed. So most likely on a quiz or a test, what I'll do is actually I'll just have you draw the Newman projection, and then I'll ask you what is the most stable conformation and what's the least stable. So the most stable is going to be when the two biggest groups are opposite of each other, and then the least stable is going to be when the two biggest groups are eclipsing each other. So that's kind of what I'd ask you. I won't probably ask you to do the full conformational analysis on an exam, but I do want you to understand what it is. Okay, convert bond line structure to the lowest. Oh, yeah, something like this would be closer to what you'd have on your exam. To the lowest energy conformation Newman projection. So there is an implied hydrogen here and here. So I'm going to go ahead and draw that in because it's just easier for me to see. And this one is actually drawn in the eclipsed notation. So I'm going to draw this first carbon. I'm looking at it from this direction. You could look at it from the other way. It's up to you, but I'm just looking at it from this direction. So my wedge is out of the page. So if I was looking from here, the wedge coming out of the page would be on my right, and then the hydrogen going into the page would be on my left. And then the CH3 is coming straight down. And then behind that, the CH3 here is fully eclipsed with this chlorine. These are also in line,